Hey everybody, so today we're going to be talking a little bit more about quadratics. Last time we introduced the idea of these quadratics as being equations that we could write off as saying we have some kind of constant, maybe an unknown number, but a number that's not going to change, we'll call that a, and we have that number of x squares, and we're adding that to some kind of number of x's, and we're adding that to some just regular unit blocks. And so these could be positive, negatives, pies, fractions, decimals, doesn't really matter, but so long as the x is being either squared or left as what we call a linear component, then this is going to fit our definition for quadratics. And the idea of it being a quadratic is really just simply saying that we can hopefully represent this using rectangles. We can hopefully be able to factor this out and get two sides of a rectangle. Sometimes we'll be able to factor it out so cleanly that we get a square. And that's what we're going to talk about today, is how can we do this when we're working with equations that are maybe a little bit more complicated. Can we relate these to squares? Now, you may have heard the phrase completing the square back in algebra, high school algebra, but the idea of completing the square is pretty hidden from most people. They don't understand why it's called completing the square. It seems to be just a series of steps that you have to do in order to get to a solution. But today we're going to discover that together, and we're going to see exactly how we can use the shape of a square to help us solve statements that are just like this. So let's go ahead and get started. I'm going to choose an easy problem to begin with, and then we're going to use the problem that we have up here as an example as a means of crafting what I refer to later as a recipe, but the math word of that would be an algorithm. It's a series of steps that we could follow anytime to be able to get a solution for what we need. So I'm going to go ahead and say, let's put this example on hold for just a moment, and I'm going to give us an easier one. Let's do something like x squared plus 6x plus 14. Okay, I think that should work out. Actually, let me change that up a little bit. Let's do plus 5. That'll be a better example for right now. And let's say that we had that equal to 0 instead. Now we might look at this and say, okay, how can we try to undo the problem the way that we've been undoing problems in algebra? And an idea that pops to mind might be that square there is quite annoying, so we should do a square root. But remember, if you try to square root an entire left-hand side, you're not able to really get rid of the square because the square root would need to affect the 6x and the plus 5 as well. And trying to do square roots across addition and subtraction is very, very difficult. It's not something you really want to play with. So that's not as straightforward of a solution as we might have thought. Okay, well, let's see if we can, again, go back to our pictures and represent this out. I have an x square, so this is going to be my x square right there. And then I have 6 of these x's. 1, 2, 3, 4, 5, 6. And then I have 5 unit blocks. So 1, 2, 3, 4, and 5. Now I'm going to try to arrange these into a square, because I know if I can arrange it into a square, I can write my original problem much more simply. How might I do that? Let's try to give us a little bit of a structure here for our thoughts. And then let's say I could put the x square at the top left. I could arrange my x's like I have done in earlier problems. Maybe I'll put 3 over here, and I'll keep that symmetry, and I'll put 3 over here as well. Okay, filling up the square nice and evenly. What about these little dots? Okay, let's go ahead and put those in here. 1, 2, 3, 4, and 5. Ooh, okay, so not so great on the dots. We need some more in order to fill up this square. How many more? Probably 1, 2, 3, probably 4 more. Well, in math, we're allowed to just make things happen the way that we want them to, so long as we balance it out somewhere else in the statement. So here's what I propose. Let's go ahead and I'll draw them in orange, because these are going to be the little unit blocks that I'm about to add to my picture. There's 1, 2, 3, 4 unit blocks that if I could add in, I would be able to complete my square. So how would I do that up here at my original statement? Well, I added 4. And if I add 4 to one side, I would need to add 4 to the other, because now I have 4 more than my original statement. If my original statement equals 0, then something that has 4 units more has to be equal to 4 units. Okay, that would work out quite well, and that would give me my square whose dimensions are x and then plus 3 on both sides. So this would be my x plus 3 square. That's another way that I could rewrite this entire thing after I add 4 to it. How can we show this with our algebra? Well, I started off with x squared plus 6x plus 5. And that was equal to 0. I then added 4, which means that if I knew that the original statement equals 0, the new statement has to be 4 more than that. So that's now x squared plus 6x plus 5 equals 4. Great. Well, this can be rewritten as the dimensions of my square. I can say that now that I've gone through all this work of turning it into a square, oh, let me adjust I made a typo here. This would now be a 9. So now that I have this as a square, I could write it as a square. I'm not changing the meaning, I'm just changing my perspective. I could write this as an x plus 3 square and say that that's equal to 4. Well, this is a much more simple in order to solve than the original. The original had an x squared, it also had another x. Now I only have one x to focus on in my work, and I just have to get rid of the square. Now, do you remember how to get rid of a square? The correct way to get rid of a square is with not just a square root, but a plus or minus square root. So let's make sure that on both sides we do a plus or minus square root. So that on the left-hand side, that's going to cancel out. We'll cancel out the plus or minus square root with the square. That gives me x plus 3 that remains. And on the right-hand side, I have plus or minus the square root of 4, which would be plus or minus 2. Well then, if I wanted to just get x alone, I would take 3 away from that side of my equation, and that would give me a deficit of 3 on the other side to balance it out. So I would have negative 3 plus or minus 2. That might sound a little bit weird. You could choose to write that as two different solutions. You could try to write that as negative 3 plus 2, and you could also write that as x could have a solution at negative 3 minus 2. Which, if you want to write it even more simply, is going to be at negative 3 plus 2 is negative 1. And negative 3 minus 2 would be negative 5. So I claim that those are my two solutions. Let's check that real quick. I'm going to change now. Let's do green. Let's do our little check here to see if this would work out. So let's do a check. And we're going to try it with negative 1 back in the original problem. So that'd be negative 1 in parentheses squared plus 6x, but instead of x we're going to do negative 1 plus 5. And the claim is that that equals 0. Well, negative 1 squared is going to be negative 1 times itself, is going to be a positive 1. Negative 1 times 6 is going to be a negative 6. And then plus 5, does that equal 0? I think so, because 1 minus 6 gets us negative 5, plus 5 gets me back to 0. That one works out just fine. Let's check if it works for negative 5. Negative 5 squared plus 6 times negative 5 plus 5. And we're going to see if this is equal to 0. Well, negative 5 squared is going to be 25 because it's negative 5 times itself, so that makes it into a positive. 6 times negative 5 will get us at negative 30. So let's see if we can erase that and make that into negative 30. And then I'm going to be adding in 5. Oh, and lo and behold, it's going to work again. 25 and then taking away 30 gets you negative 5. Adding 5 back to that does in fact get you 0. So we have two different solutions that came about from this square. That's pretty cool. Quadratics are very interesting in the fact that they do sometimes have two different numbers that act as a solution for the original problem. So now let's see if we can come up with a recipe for exactly what we just did. So we originally had this x squared plus 6x plus 5. What's the first thing we did? Well, the first thing we did was we broke our x squared into an x and an x. Okay, so that works out great. But if I'm looking to eventually solve problems like this, what do I do when there's a 2 in front? That one's going to be a little bit more difficult. What's two numbers that multiply to 2? We could do square roots, but that might make everything complicated. I'll give you a hint. We can take an entire expression like this, and we can always make it so that there is a 1 in front by just simply dividing away that a. If multiplying by a is a problem, then we can make it much easier if we just divide out a entirely. So let me show you what that would be like. So we'll say step 1, rewrite ax squared plus bx plus c equals 0 as, I'll fix up that equal sign there, rewrite it as x squared plus b divided by a, x plus c divided by a equals 0. Did I change something there? Did I make it incorrect? Is it no longer true? Well, I'll tell you what I did was, behind the scenes, I just divided out that a. So I divided out everything on the left-hand side by a, and I divided out the right-hand side by a in order to keep it balanced. Well, if I divide out the first term by a, that just causes these a's to cancel. If I divide the second term, that b by a, I just get b divided by a. That looks pretty okay. And then I have c divided by a, that gets me c divided by a. So long as I divide each and every part of the left-hand side by a, I should have maintained my meaning. So now I've gotten it where I always have a number 1 in the beginning, and so that makes the first part of my solving out my square much easier. Okay, great. So now we've got this x squared plus b over ax plus c over a equals 0. What was the next thing that we did? Well, let's take a look back over here. We had 6x, and I wanted to take my 6x, and I wanted to put half of it on the top side of my square, and I wanted to put the other half of it on the bottom, or on the left-hand side of my square. So I kind of got both of those sides. Okay, well that would be taking my middle term and then dividing it by 2. Okay, so that would be taking the new middle term, this b divided by a, and dividing it by 2. Let's write that out. So now I have b divided by a, and I could say divided by 2. But if divided by 2 just means put it on the denominator, I'm going to rewrite it like this. b divided by 2a's. And this is the exact same meaning. This is the same thing as b divided by a divided by 2, because the 2 is on the denominator, and that's where division goes. Okay, great. So now I've got my b divided by 2a. That means that I've essentially found my little 3's here, if I were going back to our previous example. Okay, then what did we do? Well, if we remember back, we started with this other 3, and we said we really wish that there were 9 down here. And we wanted there to have been 9 because that was what 3 times 3 was. So maybe that's our third step. Find b divided by 2a, and then square it. Now, we're starting to get into some really complicated things, but keep in mind what the meaning was. It was take this nice new middle term, and then use half of it on the top and half of it on the side to figure out what I need for completing my square. Oh, notice the completing the square verbiage. That's going to come back up in a little bit. Okay, great. Then what did we do? Well, we grew, or I guess you could have shrank, our c value, or our last value, I guess now it's c divided by a, our c divided by a value, to get b divided by 2a squared. Now again, if this feels like this is starting to become overwhelming with the symbols, go back to the meaning. This is really what algebra helps to teach us to do, is to not worry so much about what's in front of us, but to keep track of this model of logic, this story problem that we're telling ourselves. All we're saying is that if I have a nice number here at the end that corresponds with having a 1x squared, I can use this 5 as my 5 little unit blocks, and I just want to have made these 5 unit blocks into a perfect square. So that's what we're trying to do, is we're trying to grow c divided by a in order to get that square. Now, once we've done that, we should be able to rewrite this entire thing as x, and then we would need to figure out what goes to the end part. We'd have x plus b divided by 2a squared, and then we would have that would be equal to some extra, right? Either what we had to grow or what we had to shrink on both sides. We either had to add into our picture to get a perfect square, or we had to take away in order for it to be a perfect square. Okay, so this is what we would call in industry a dynamic document, and I worked with these a lot whenever I was trying to develop work plans for people. So this is something that you're really going to want to get comfortable with for your future job. And I'll show you why we call it dynamic. We call it dynamic because now that we have our idea for how we would use this, we're going to test it, and then once we test it, we're going to be able to see if we need to add anything or change anything. Okay, so let's go ahead and try it with this really complicated problem that we had at the top, this 2x squared plus 5x plus 10. All right, so we know that we have 2x squared plus 5x plus 10. first step. First step says that we were going to try to divide away that leading coefficient, that number 2, so that everything became a little bit simpler. So that would be 2x squared plus 5 over 2x plus 5, and we knew that that equals 0 from our original statement. Okay, good. So far, so good. Step 2 was find out what this b divided by 2a was. Okay, so that means that I already have my b divided by a. That's my 5 halves. That's when I started with my b, and then I divided away a. And now I just need to divide it again. That would be, well, 5 over 4. Okay, that's not too bad. Step 3, we need to take that and we need to square it. Okay, well, squaring it just means that we multiply it by itself. So that would be 25 on the top from 5 times 5, and 16 on the bottom from 4 times 4. So far, so good. All right, now we should have all the tools we need in order to try to turn our original problem, or at least this more simplified problem, into a perfect square. How would we do that? Well, we have x squared plus 5 halves x, and we would need to grow or shrink this 5 to get 25/16. That sounds pretty difficult. I don't know that I want to do that. That sounds like a lot of work. I'll give you a secret what we can do instead. Let's go ahead and instead write this as 25. Let's put the 25 over 16 right here. This is what I would have originally wanted to get to. So why don't we just start with the end? We'll just say I'm going to put 25/16 over here. That's going to be the part of the square that I was going to be missing anyways. And then I'll just simply say that I'm going to move this 5 that's in my way away. I'll move it over here. Take a moment and take a look at what exactly we did there. We took the 25 over 16, that was what I would have wanted to grow or shrink down to, and I said, nah, actually in math I have a better option. I can just introduce things that are going to make my life easier, so long as I balance it out. So I introduced what I wanted to have over here, and then I just moved the 5. Oh, and I guess I would need to keep things balanced, wouldn't I? So I'd actually have needed to, on the right-hand side, also added 25 over 16 to keep everything nice and balanced. So we could rewrite all of this as x squared plus 5 halves x plus 25 over 16 equals, let's see, negative 5 plus 25 over 16. If this feels weird, feel free to call me over and I'd be happy to talk to this part of the video. But just as a reminder, what we're trying to do is make the left-hand part be something I can make into a perfect square and have the right-hand side just be something that I can figure out later. Okay, good. So we have x squared plus, okay, well, we now have all the tools we need to make a square. Let's try to make our square. I know x is going to need to be first. I know I'm going to need something that multiplies to 25 over 16. That's going to be my 5 over 4. Notice it's the same thing we were prepping for right at the beginning, and that's going to be able to make my square. On the right-hand side, I have 25 over 16, and I'm adding that to negative 5. I could do that with common denominators. That would be negative, let's see, if I multiply 5 by 16, that would be negative 80. So this could be rewritten as negative 80/16, and I could add that to 25/16. Okay, so what this says is that I have x plus 5 over 4 squared equals a negative 55 over 16. Now this is actually as far as we need to take this problem, because now I can already tell that before I move forward, I have a problem that's not going to make any sense. How can I have a square, something that I create by multiplying a number times itself, that turns out to be negative? Can't ever happen. So I actually know that without going any more into this problem has no solution. And that would have been a very difficult thing for us to have seen if we hadn't started with this other example and made all of our rules underneath. So let's go back to our rules and see if we can flesh these out a bit. Rewrite this entire thing as dividing away the a. That worked out quite well. That made it so that the first term wasn't a problem for us. And then we had find b divided by 2a. That was when we were again trying to fill up the top and the right hand side with these little x amounts. Okay. Find the square. That was the goal that I wanted to get to in the bottom right hand side. The growing or shrinking we didn't really do. So let's see if we can't put a line through this one and be a little bit more truthful to what we worked out for us in the problem above. What we did instead was we moved the c plus a, this little tag along number, our 5, we moved c plus a, or c over a, move c over a to the other side of the equal sign. And then, in order to get that part of the square that we really wanted, we added the b divided by 2a square to both sides. Then we were able to rewrite it as x plus b divided by 2a squared equals, and we could be a little bit more clear with what we did over here. On the right hand side, there wasn't just this extra. We had the original c that we had moved over, this original c over a that we had moved over, so equals negative c over a. That's what happens when we move it over. And then what happened was that we had added b divided by 2a squared onto both sides. Ooh, there's a lot that goes into these problems, but that's why you really want to take time to flesh out these steps. These steps are going to help us when we're trying to solve large problems like this by doing a lot of this rearranging. How do we capture that in our notation? So after you go through here and clean everything up, we should be able to have something that looks like we start by dividing by a. Next thing we do is we try to break up our middle term into halves. We use those halves to create a square. We introduce that square to both sides and then make sure that we have nothing but a square on the left. And from there, we can pretty much work our algebra on down. Lots to go through on that. Let me know if you have any questions. Okay, we now have all of the tools that we would need in order to tackle creating the quadratic formula. And you may have heard of the quadratic formula before. For those of you who don't know it, there's a rhyme that goes along with it. I will sing you the rhyme. Here's the quadratic formula if you were just told to memorize it before. It's negative b plus or minus the square root of b squared minus 4ac all over 2a. There's so much to unpack here. This is so much to try to learn that if you're intimidated, it's completely understandable. You have symbols moving around, you've got square roots, you got a plus or minus, you've got opposites, negatives, divisions. There's so much going on here. The thing I want to do is just kind of present this for those who remember this when they were told to memorize it in high school. And for everybody else, we're about to create exactly where it comes from so that we're all on the same page. Now, there is a rhyme that goes along with this one, and it goes to All Around the Mulberry Bush. So if you're familiar with All Around the Mulberry Bush, or the song that's normally played when you're turning the crank on a jack-in-the-box, it goes a little something like this. Opposite of b plus or minus the square root of b squared minus 4ac all over 2a. It's a silly rhyme, but I'm telling you, even to this day, it helps me remember the full formula. So it's just as if you're singing it to All Around the Mulberry Bush. Opposite of b plus or minus the square root of b squared minus 4ac all over 2a. Okay, we're going to see exactly where that comes from. Well, it comes from whenever we're trying to solve questions like this, what we were just working on was completing the square and trying to let that be the method. Would it surprise you that completing the square and the quadratic formula are the exact same thing? Let's see where that comes from. I'm trying to solve out for x squared. Let's see if we can do this all with symbols now. So I'm going to say step 1, same thing as before. Divide everything through by a. That gets me something that should hopefully be a much simpler problem to work with. I know it looks like it has more with the fractions, but keep in mind if these were numbers, hopefully there'd be some simplification we could do. All right, next thing. X squared plus b divided by a. Remember that in our original steps, we moved the c over a away so that we could make that be a little bit easier. So we would say x squared plus b divided by ax equals negative c over a. That's when we move it across. Next thing we did, we introduced those unit blocks that allowed us to create a perfect square. How did we find those? Well, we didn't change any of this. What we did was we split the middle x blocks into halves and then use that to create a square. Okay, well, let's do that. Split this into halves, so now it's over 2a, and then use that to create a square. And if you add it to one side, we've got to do it to the other side too. So this is b divided by 2a squared minus c over a. All right, next thing we could write it as a square. That's why we did all of this work. So now we've got x plus b divided by 2a all as a square equals b squared divided by 4a squared. Where did that come from? I multiplied that entire first thing by itself. So I multiplied b by itself and I multiplied 2a by itself. That gets me b squared on the top. 2 times 2 is 4, and a times a gets me a squared. And then I have my minus c over a. All right, keep going. I need to undo this square now. How do I undo squares? With a plus or minus square root. Okay, so now I have x plus b divided by 2a equals the plus or minus square root of b squared divided by 4a squared minus c over a. This is the part where, if you let it be, this can actually be a pretty fun part of math, where you realize that you have the power to move everything around, no matter how complicated it is and how challenging it is. So long as you understand what you're allowed to do forwards and backwards from that model, there's no reason you can't create horribly complicated looking problems that you understand where they came from. Don't worry, this is actually going to get even easier. If we want to solve out for x, maybe I need another one here. Did I forget a step? Looks like it. We're going to need to add in another one. We'll do step 6. This would be x equals, we'd need to get x alone, so we're going to try to take away this b over 2a. So I'm going to try to take it away from both sides. That would be plus or minus the square root of b squared over 4a squared minus c over a minus b over 2a. And that is a way that we could solve every single time. If we start with an equation, you can just grab a's, b's, and c's from our original number, and we could throw them all into this and we could get it solved. So for example, if I gave you the problem of 14x squared minus pi x plus square root of 13, you have your a, your b, and your c that you could throw into this formula and you would get an answer. But this seems very different than our quadratic formula. Maybe, but do you see some similarities as well? I'll help kind of show you some of them. Let's work with just this first part here. How can we rewrite all of this a little bit more simply? Well, we could use common denominators. So let's go ahead and write that out. Again, this is not something that you have to be able to memorize. This is not something that you have to worry about recreating on the spot, but it's something that I want to kind of show you because it's really cool to know where these formulas come from and that it's from the same shapes we've been studying. Okay, so we're working with trying to get common denominators. So I need to put a 4 and an a on the bottom to get 4a squared. So I could put a 4 and an a on the top to keep everything balanced. That works out quite well. Well, now I have b squared minus 4ca. I would rather write that as 4ac. Okay, so now I've got plus or minus the square root of b squared minus 4ac over 4a squared. Well, I could actually rewrite that one. There's no reason I can't square root just the bottom. That would actually be a pretty easy thing to square root. So let's see if I can't do that. Square rooting 4a squared says what times itself gets me 4a squared? That would be 2a. And then I have the minus b over 2a as well. Well, I can actually, those are the same denominator. I've got 2a in both situations. It's a number, it's a weird number. It might be difficult to see exactly what that number would be, but there's nothing to say that I can't combine these all into one fraction because I have 2a on the bottom of the first and 2a on the bottom of the second. And notice what we've created. We've created our original formula. Opposite of b, the negative b, right here. Plus or minus, that's right here. The square root of b squared minus 4ac, that's right here. all over 2a, because all of it is over 2a. So what I'd like to have move forward from here is keep this in your notes. This is something to reference and to remind yourself that you can understand where all of these formulas come from, because they come from simple tools that somebody just explored through all the complications and made sure that everything that they were doing along the way made sense. So, but if you would like to, you now have my permission to just simply memorize the formula and use it moving forward. The quadratic formula is opposite of b plus or minus the square root of b squared minus 4ac all over 2a. And that would be equal to x. And we can use this whenever you have something of the structure ax squared plus bx plus c equals 0. Now, why would we have wanted to do all this? For the same story that I think I told you before. When I was working in industry, there was a time when every single time I would go into work, my boss would say, okay, we have so many orders, we have 800 orders, how many people do we need to bring in? And I would go back to my desk and I would do some calculations and I'd say, we need to bring in 4 people and somebody for a half day. And the next day he'd say, okay, well today we have 936 orders, how many people do we need? And I'd go back and I'd do the same calculations, and then I'd come over and I'd say, okay, well now we need this many people, we need 9 people and somebody who can kind of shift over from another department. Every single day I would be asked this question, and eventually what I created was just a program that I could hand to him, and I could say, here you go, this is something that at the beginning of the day you can type in how many orders we have, and it will tell you how many people we need. This is sort of that same idea, where now, instead of trying to solve every single problem with a shape, with a reference to a previous problem, we have a program. Our program is called the quadratic formula, and it's a method by which we can solve any type of quadratic problem easily by just grabbing the elements of it and putting in a way that we know is true to the original form. Let me show you how powerful this is. Let's try to solve this very last problem together. 3x squared plus 2x minus 2 equals 0. Now, keep in mind that we could represent this as shapes. We could represent this as these little rectangles. We could try to factor. We could try to square root. Or, because we've already done all of that effort through the original part, we can just take advantage of all of our labor. This is going to be a. A is 3, because it's the first letter. B is going to be 2. C is going to be negative 2. Now we just put this into our quadratic formula, which we can remember with our song. Opposite of b, that'd be negative 2, plus or minus the square root of b squared, that'd be 2 squared, minus 4ac, so it'd be minus 4 times 3 times c, all over 2a, that'd be divided by 2 times 3. And we can just move this all the way on through and use our calculator to assist. Negative 2 plus or minus the square root of 2 squared would be 4, minus 4 times 3 is 12, times a negative 2 gets me a negative 24, so a negative negative gives me a positive 24, and on the bottom I have 6. So in 3 lines of work, I was able to say that in order to solve this problem, you've got 2 solutions. One, when you start with negative 2, and you add the square root of 28 to it, and divide by 6. And the other, when you start with a negative 2, and you subtract the square root of 28, and divide by 6. That's pretty cool. That's really quick. That's what happens when we take time to go through all of that effort of creating a formula. Now we can actually simplify this up a little bit, because notice that 28 can be factored. So if we want to do a little bit of scratch work here, we can say 28 can be factored into 2 and 14, which can be factored into 2 and 7. So we can actually rewrite this even more simply. Negative 2 plus or minus 2, because there's a 2 times 2 here. That's a square, so when I square root it, that undoes it. So I have 2 times the square root of 7, the 7 left over from our factor tree, all divided by 6. And since everything's doubled on the top, I can cancel that away with undoubling the bottom as well, right? We call that factoring. I can factor out a 2 from the top, and I can factor out a 2 from the bottom. And I could say that that's equal to negative 1 plus or minus square root of 7 over 6. And that would be my final answer. So today has a lot of very powerful lessons. The most important being, don't get intimidated necessarily from having a lot of variables moving around or a lot of these procedures or having to explore through our problems. It's okay if what we're doing is immediately complicated and it's a little bit intimidating. By pushing through that and getting to something that is maybe looks intimidating but contains within it a lot of work, we can save ourselves time in the future without having to go back to square one every single time we see a similar problem. The quadratic formula is now something that you can keep in your tool belt. You can pull it out without justification and say, I have a quadratic equation, I can solve it with my quadratic formula that I spent a lot of time and effort modeling and logicking through, so I can just simply get you to an answer much more quickly.